Welcome back, class. So this is the last topic of organic chemistry, and that is halogen family. 17th group member we are talking. So the other members of the 17th group: fluorine, chlorine, bromine, iodine, and astatine. Electronic configuration, if we discuss, 1s2, 2s2, and 2p5. For fluorine it is 2p5, and so as for chlorine till 3p5, 4p5, 5p5, and 6p5. We'll start the discussion with the properties of halogen. Properties of halogen. So the very first property is variable oxidation state. Variable oxidation state. As we had discussed in our previous lecture, the variable oxidation state. So how it will find, except the first member, that is the fluorine, because it cannot extend its valency because of the unavailability of d orbital, but from chlorine, bromine, and iodine they can do so. Well, as the size increases, it can extend its valency. So let's take the example. You can take anyone. If you go for the chlorine 17, so the last electron will be entered in 3s2 and 3p5. 1, 2, 3, 4, and 5, and this is the vacant d orbital. So this is 3s2, this is 3p5, and this is 3d. So here we have only one unpaired electron, so oxidation state will be +1. Then for the first excited state, what will happen? The paired electron from p orbital, one of the electron from p orbital will jump to the d orbital. Okay, so here we have paired electron, here one of the electron will shift to here. So this is called first excited state. In this case we have 1, 2, and 3 unpaired electrons, so this will show +3 oxidation state. Similarly, we can go for the second excited state. In this case, what will happen? Another paired electron from p orbital. We have one more p electron paired in p orbital, this one, so this will jump to d. So here we have one more electron in d orbital. In this case we have 1, 2, 3, 4, 5, so the oxidation state will be +5. There is one more possibility, so we'll go for the third excited state, because as p and d orbitals are available at the same energy level, third, so we can go for the first excited state, then second excited state, then the third excited state. Now in this case the electron will jump from s, the paired electron we have in s orbital, so one of the electron will jump to the d. Okay, so here we have 1, 2, and 3. So in this case we have the 7 non-pair electrons, so here we have +7. So this is how it shows the variable oxidation state. Only fluorine, which is the most electronegative element, will show -1 oxidation state. Okay, only fluorine, every time it will show -1. Rest of the halogens will show -1, sorry, +1, then +3, then +5, then +7. Only in case of fluorine it will show -1. So this is the first property. Moving ahead, the second property, and thus it is the oxidizing agent. Fluorine is most electronegative, so is fluorine is strongest oxidizing agent. It will act as a strongest oxidizing agent. So in while the iodine will weakest. Sorry. This is the second one. Then the third one, the third property. This property is based on the bond length. We all know that the bond length and bond dissociation energy relationship. Bond dissociation energy is inversely proportional to bond length. Higher the bond length, weaker will be the bond dissociation energy. And this is what the region, as we move down the group from fluorine to astatine. Astatine is uh, fluorine to astatine. What will happen? The size will increase. So as the bond length will increase, so the order of bond length is HF, then HCl, then HBr, and then HI. So this is the order of bond length. And if the order of bond length like this, what will happen with the bond dissociation energy? So the order of bond dissociation energy will be reverse. So HF required highest bond dissociation energy, then HCl, then HBr, and then H. So this is how they relate with each other. One more property we can discuss on the basis of the bond dissociation energy, and that is the acidic character. Acidic character. The order of acidic character. Okay. So acidic character, again, if the bond breaking is very hard in HF, it will not donate this proton very easily. Whereas in this case, the bond breaking is easy because of the higher bond length. So donation of proton is easier here. So the acidic strength in this case follow this order: HF, HCl, then HBr, and then HI. And again, we are discussing this by the reason of bond dissociation energy, because the bond dissociation energy is very less in case of HI. There is one more property, that is thermal stability. Thermal stability. This again a phenomena of bond dissociation energy. Okay, because in this case the highest bond dissociation energy, so the thermal stability is highest in this case. So here the order will be again HF, HCl, HBr, and HI based on the bond dissociation energy. So we can discuss several property based on the bond dissociation energy. Now last property is electron gain enthalpy. Electron gain enthalpy. This is one of the important, and so many times the questions asked in the competitive examination, what is the order of electron gain enthalpy? Electron gain then is tendency to attract the electron, got it? But as we know that the fluorine is the most electronegative, so fluorine should be the strongest electron gain enthalpy, but it is not like that. Here the chlorine is the stronger one compared to fluorine. This is the difference. This you should remember always. The chlorine is the strongest electron enthalpy, and here the reason is smaller size due to a smaller size of fluorine. It is not in traditional manner. Okay, so this is the different properties of halogen. We had started this lecture. This is the lecture number 1, and we will complete this in 2 lecture. This is the lecture number 1 of halogen family, the 17th member group, and we had discussed some properties, that variable oxidation state, then the oxidizing agent, then the bond dissociation energy, and based on the bond dissociation energy we had discussed the several properties, acidic character and thermal stability, and finally the electron gain enthalpy, which is very important. So you should keep this point. Now, as per your syllabus, we have to discuss the oxoacids also. So it's time to discuss the oxoacids of halogen. Oxoacids of halogen. So again, we'll do this discussion with the help of the oxidation number. As I told you earlier, the oxidation number, then the common name, then we have fluorine, chlorine, bromine, and iodine, and we have the oxidation number +1, +3, +5, and +7. So starting with the very first, that is the +1 oxidation state. The common name in the case of +1 oxidation state is hypohalous acid. Common name is hypohalous, OUS. First is the oxidation number acid, hypohalous acid. So what is the other one? HFO, HClO, HBRO, and HIO. So as the common name is hypohalous acid, so what is the name of this? This will call hypofluorous acid. This is hypofluorous acid. Similarly, this is hypochlorous acid, this is hypobromous acid, this is hypoiodous acid. Then the second one with the +3, this is halious acid, HALOUS, halious third acid. So here we'll go for some example of halious acid. In this case there is no, because it has only one oxidation state, so this there is no example. In case of fluorine we'll go for SClO2, in case of chlorine, and no other example will form. Okay, SClO2. So in this case, what will be the name? It is chlorous acid. Chlorous. It is chlorous acid. Then the third is the +5 oxidation state. Name is halic acid. HALIC, halic fifth. Halic fifth acid. So again we'll take the example. Here the example HF is not possible. SClO3, here HBRO3 and HiO3. So this is what? Chloric acid, bromic acid, and iodic acid. Chloric, bromic, and iodic. And the last one is called perhalic. Perhalic, and the oxidation number is 7. acid, perhalic acid. So again, no example in case of fluorine, but we have HClO4 in this case, HBrO4 in this case, and HiO4 in this case. So name, this is called perchloric acid, this is perbromic acid, and this is periodic HiO4. You must remember the use of this periodic acid in the oxidation of polyhydric alcohol. Polyhydric alcohol, if you remember the alcohol chapter, the polyhydric alcohol is oxidized with the help of periodic acid HiO4. So this is the use of this. So this is how the oxoacids of a halogen is decided. And as per your syllabus, we have to discuss the hypoacids of chlorine. Okay, rest of the is very simple. So this we need to discuss. We will discuss the structure, we will discuss different oxidation state and the acidic behavior also. So this HClO, HClO2, HClO3 and HCl4. So next we will talk about the structure. So the structure of, as per your syllabus, we will discuss only high chloroacids compound. Okay, so here we have the very first structure, and that is the HClO. So we will draw the structure like this, HOCl. Okay, so HOCl, then again same HOCl. The total valence electron will be 1, then plus 6 for oxygen, plus 7 for chlorine. This will give 14 electron. Okay, we have two bond pair, so bond pair electron is 4. Then we have a lone pair counting, so what we can put 3 lone pair here and 2 lone pair here, so total 5 lone pair, that means 10 electrons, so total will be 14 electron. Okay, so this is how the structure will draw. Now every time while the addition of oxygen, we will put oxygen with double bonded here, one lone pair, then the second lone pair, and then the third lone pair. Okay, so we'll go for the second structure, and that is the HOClO or HClO2. So we will draw a structure H, then one oxygen, then chlorine, no doubt about this. Then we have double bonded oxygen, one oxygen will put. So how many lone pair remaining here? 1 and 2 at chlorine. Then 1, 2, 3, 4, 1, 2, 3, 4. So here again we will calculate the, this is HOClO. Total valence electron 1, 6, 7, 6. So this is 20 electron. Okay. Bond pair total electron 1, 2, 3, 4, 8, and lone pair 4 here, 4 here, 8, and 4 here, 12. So total is 20 electrons. So this is the correct structure. Then in the third case, what will happen? Another lone pair will be oxidized, and we will get another oxygen. So here double bonded O, double bonded O. So in this case, we have one lone pair left here. We will put two lone pair here, then two lone pair here, two lone pair here. So this is the formula of HOClO2. Okay, we will calculate the total valence electron in this case. So in this case we have 1 plus 6 plus 7 plus 6 to 12. So total will be 26 electron. Okay, And in the 26 electron, bond pair electron is 1 2 3 4 5 6. Total bond pair is 12. Lone pair 4 4 4, 12 and 14. So again this structure is correct because lone pair bond pair combination is correct. And we left with one structure. So H O Cl, double bonded O, double bonded O, and double bonded O. So now the three lone pairs at the chlorine is complete by the three oxygen atom. So the formula here is HOClO3. Total valence electron in this case 1 plus 6 plus 7 plus 18. So the total will be 32 electron. And bond pair, the bond pair we have 1 2 3 4 5 6 7 8. So total 16 bond pair, and lone pair 4 8 12 and 16. So 16 bond pair and 16 lone pair, this will give you 32 electron. So this is how the structure is drawn. Now the relative acidic strength. The relative acidic strength. So as we know that as the oxidation number increases, the relative acidic strength is increases. So here the oxidation number, we are talking about chlorine because the central atom is chlorine. We are talking about the oxoacids of chlorine. So here the oxidation number is +1, here it is +3, here it is +5, and here it is +7. So what is the order? Order is very simple. HOCl, then HClO2, then HClO3, and then HClO4. As per the increasing oxidation number, this is the acidic strength. But there is an explanation. We will go for this explanation because so many times we are talking about that as oxidation number is increasing, the acidic character is also increasing. So what is happening, we will discuss in this explanation. Well, this explanation is based on a concept, and that is called Lowry-Bronsted concept. Lowry-Bronsted concept. And that was what? Stronger acid has a weak conjugated base, and so is the vice versa. Okay, so in this case the stronger acid is HClO4, so it has a weakest conjugated base. Reason is what? And how we will find the conjugate base? By the removal of proton. So by the removal of proton, in this case the structure is OCl with lone pair, and here is a negative charge. In this case Cl double bonded with O and singly bonded with another O which has a negative charge. Next case Cl double bonded with O, then another double bonded with O, and with the one oxygen with negative charge. Next case Cl double bonded with O, double bonded with O, double. Forget about the structure, I am talking about the electronic arrangement only. So this is how the conjugated base written by the removal of a proton. What is actually happened here? In the first case, this oxygen which contain a negative charge is distributed by only oxygen or carried by only this oxygen. But in the second case, this is ClO negative, this is ClO2 negative, this is ClO3 negative, and this is ClO4 negative. In the second case, this oxygen negative charge can be carried by this oxygen also, because of the resonating structure. This oxygen also resonance stabilized, so this negative charge distribution is increases in the second case. Similarly, it is also increases in the third case with the availability of the two oxygen, and it is maximum in the third case. So reason is what? Charge distribution charge distribution is maximum in ClO4 negative, and so as stability also. If the charge distribution is maximum, stability is also. So this is the order of stability. This is the order of this, has maximum stability. Okay. So because of the stability, what will happen? The availability to donate a proton, sorry, to attract a proton, it has a lesser attraction for the proton. It has lesser attraction for proton. If it has a maximum distribution of this negative charge, it will be more stable, and if it will be more stable, then it has a lesser attraction for proton, and if it has a lesser attraction of proton, it behaves as a weak base, because the uh, non-availability of attraction of protons, so it will behave as weak base. Okay, so reason is clear. Charge distribution is maximum because of the availability of three oxygen. The charge will distribute evenly, maximum to in this case, lesser in this case, much lesser in this case, and very weak in this case, so that the lesser attraction towards the proton, and it will be have a weak base. If it is not attract the proton, it is a weak base. So this is what the reason that the HCl4 is the maximum acidic. So this is how you need to explain the reason. So this was the first acidic character we had discussed. Then the second, here the based on the different oxidant state, the oxidant state is different in every case. +1, then +3, then +5, and then +7. Okay, but if the oxidation state is same, what will happen in that case? So the second is when oxidation number is same. So example, we have HClO, HBrO, and HIO. I'm not doing the HFO because very smaller size, it will not easily it can form. So only three. So in this case, what will be the order? Here the central atom are the halogens, and in every case the oxidation number is same. Here the oxidation number of fluorine is +1, here again +1, and here again +1. In this case, we'll go to check the electronegativity behavior. Electronegativity is maximum for chlorine. Of course, the electronegativity order we had already know: fluorine, chlorine, bromine, and iodine. So the highest electronegativity is of chlorine. So based on the electronegativity, the highest acidic state is for HClO. Why it is happening? See, we will take the two cases. First is the HOCl. In this case, this Cl is more electronegative. So what will happen? It will attract electron from oxygen. That means it has greater tendency. It has greater tendency to withdraw electron, and if it has greater tendency to withdraw electron, what will happen? Here the electron density will be reduced, and here if the electron density will reduce, proton can easily donate. In this case, proton easily donate, and because of this it is a stronger acid. Let's take another example, that is the HOI. Here the electronegativity of oxygen is lesser. So here what will happen, it has lesser tendency to withdraw electron. Okay, and if it has lesser tendency to withdraw electron, the proton will not easily donate. Proton is not going to be donate very easily. So here proton is not donate easily, and that is why the HIO is not as stronger as compared to HCl. This is what the reason in this case. So we had discussed two examples of relative acidic strength. First of example is based on the different oxidation state, so this concept is clear by the conjugated base concept. And the second one, when the oxidation number is same, so this is based on the electronegativity. So this is all about from the halogen family first lecture, where we had discussed the uh, various properties of halogen and oxoacids of halogen. Okay, now we are going to end with this question, and question is why, very simple question, you can answer very easily. Why fluorine forms only one oxoacid, that is HOF. Why fluorine form only one oxoacid? Reason you have to write in the comment box or WhatsApp to my number. That is, so this is very easy question, you can easily answer that. Thank you so much for your